Welcome to the OpenSystems Media eCast titled Military ISR Sensors and Embedded Signal Processing. My name is John McHale, Group Editorial Director with Military Embedded Systems and moderator for today's event. Our speakers today are David French, Director of Business Development at Abaco Systems, Marc, Senior Product Manager at Curtiss-Wright, and Rodger Hosking, Vice President and Co-Founder of Pentek. Now, before we get started, I have some short housekeeping announcements. This and all OpenSystems MediaCasts are copyrighted and may not be recorded or used in any way without the express written consent of OpenSystems Media. This eCast will consume about 35 to 40 minutes, leaving the remaining time for the question and answer session. I want to point out some important buttons on your screen before we get started. First, please take note of the Enlarge Slides button. By clicking on this button, you'll be able to view the slides in full screen mode. You can also use the Download Slide button to view the slides as a PDF to see them larger. The second important button is the Forward to a Friend button, which enables you to email a friend to register for the event. The third button on your console window enables you to enter questions in real time, and we will do our best to address those questions during the closing Q&A session. If you have a specific question intended for a specific speaker, please note so at the beginning of your question. Otherwise, we'll hand out the questions equally to all our speakers. If you have a question pertaining to the eCast operation itself, one of our technicians will get back to you after the eCast with more information. This eCast will be archived online and be available for 1 year. There will also be an MP3 version of the event available. Now I'm pleased to turn it over to David French. David, please advance your slide.
Thank you, John. And again, Abaco appreciates the opportunity to present to the attendees today. And as the industry and the DoD continue to drive future ISR system design and development, and considering the topic of this webcast, it's an appropriate opportunity to discuss the recent stand-up of the Sensor Open Systems Architecture Consortium, or SOSA we call it, managed out of the Open Group. It's similar to the FACE Consortium Future Airborne Capability Environment level of activity. So my discussion today will be an introduction to SOSA. So my name is David French. I'm Director of Business Development for Abaco Systems. And for those perhaps not aware, we were a former business unit of GE Intelligent Platforms and divested from GE late last year. We are essentially the same organization, but with renewed focus and energy, and we're a rapidly growing team. We've been serving this defense and aerospace embedded computing market for some 30 years or more now. Our portfolio covers the spectrum of embedded computing products in open industry standard form factors. A VME bus is still very much part of this portfolio as this compact PCI, but much of our new product development is in open VPX form factors and mezzanines. The portfolio includes front-end signal processing, video processing, single-board computers, high-performance embedded computing, GPU co-processing, networking, and avionics bus I/O. And beyond that, we also offer integrated chassis systems from small form factor solutions up to platforms and the teraflops of performance. We further offer a pretty powerful multi-processing integrated software tool suite called Axis that enables development of highly complex multi-processor systems supporting open software standards and optimized library versions with open standard APIs. So among the themes of the webcast are IR systems tactical or operational superiority and open systems design. So ISR systems are a cornerstone to situational awareness and enable operational superiority. With open systems architectures and a strong ecosystem of solutions, which you're going to hear a little bit more about subsequent to this presentation, designers can leverage ever-advancing commercial silicon technologies to empower ISR system developments with ever-increasing capabilities. There's some very interesting and exciting technologies just on the horizon that will address not only raw performance at the high end, but also drive significant overall performance and functional density at significant reduced size, weight, and power. So because IR systems directly support the new DoD offset strategies, there is a constant demand for more capability, and in particular, faster deployment of new or more integrated capabilities. So with the value IR systems offer, they are growing in number, complexity, but with a concomitant additional cost. So keeping up with the demand, enabling faster deployment, offering flexibility and reuse of developed products, technology, and capabilities, all the while addressing cost, the end user community stood up the Sensor Open Systems Architecture Consortium under the auspices of the Open Group. So SOSA is driving adoption of existing relevant industry standards for ISR developments and new standards if necessary, and a little bit more on this in some subsequent slides. So it's still very much in the early stages and has been coordinating activities with the FACE Consortium, but SOSA will soon eventually formalize into a standalone consortium in its own right. So it's specifically designed and administered to be vendor neutral between industry and government. It's intended to drive collaboration toward the stated end goals. Again, very much similar to the FACE Consortium activity developing a common avionics operating environment, if folks on the call are familiar with that level of consortium activity. So SOSA includes both hardware and software and is governed by the following working groups you see here. So the enterprise and business working groups coordinate overall consortium activities and drive documentation products that enable industry to develop and innovate within those defined industry standards. And the government to solicit and more affordably procure these new ISR capabilities with better time to deployment. So I think notable here perhaps is the intent to address not only interoperability and reusability at the embedded hardware level and software operating environment, but physical electromechanical portability across multiple platforms, the objective being the ability to install subsystems on multiple platforms. So this depiction actually borrows from material put together by Dr. Ilya Lipkin of the Air Force Lifecycle Management Center and a principal driver behind SOSA. In the upper left, point solutions and workarounds are often the means to meeting current ISR mission needs. Without some level of portability in any of these solutions, new mission requirements often require significant reengineering to effect a solution, and then at considerable cost. So by decomposing relevant hardware, software, and electromechanical interfaces into interoperable and industry standard interfaces, which you see in the upper right, it then becomes possible and ideally more efficient to recompose those building blocks into a more affordable solution to get maximum reuse of developed capabilities. So those common elements and interfaces will also be developed to allow system designs to bring together or fuse sensor suites across multiple modalities. So this is a primary objective of the SOSA consortium. So how does it work? So the SOSA process engages all the working groups that you saw previously and industry participants, including the government, toward this decomposition to identify the technical standards that ultimately support more efficient and impactful ISR systems designs. And effective reintegration and deployment of existing assets. So from a common reference architecture viewpoint and any type of sensor modality, key interfaces are defined, and through an iterative process with the team, the end product is to define technical standards for future ISR system developments and application. So this diagram depicts the boundaries within which the consortium is defining these open standards and illustrates the consortium focus at the simplest of interface boundaries, the SOSA realm with an adopted vernacular there. As you can see, it notionally shows analog and digital interfaces, power, of course, and physical interfaces are applicable depending on the system. So a system could be one sensor, one modality, or multiple sensors with varying levels of integration and fusion as demanded. And SOSA is likely to adopt other supporting standards, such as FACE, Future Airborne Capability Environment, the Army's Victory Convergence Standards, Open VPX for hardware, modular open radio architecture, SPIE standards, hardware open systems technology. So there's already a group of standards that are likely to support this, and the objective, again, is to converge these so that again, the ability to get reuse out of existing capabilities both on the hardware domain and the software domain, So conformant contracting. So in addition to defining technical requirements and applicable interface standards, the SOSA Consortium is also developing contracting documentation accompanying products to support future ISR SOSA conformant contracting. So the program offices will eventually have the tools necessary to effect IR systems acquisition backed up by a conformance verification process. So early versions of the business guides have been published, and they're to reinforce a shared vision within SOSA and what the consortium will be and how it will operate to meet those goals. And once we have successfully transitioned from an initiative under FACE to a standalone consortium, a more definitive SOSA business guide will be developed, along with companion SOSA contract guide. So again, there's two sides to this. There's the customer, and there's the industry that's developing capabilities and providing innovation. So my last slide. So today it's still very much a work in progress. There's a lot going on behind the scenes. In fact, there's a SOSA proof of concept effort underway to demonstrate SOSA central tenets in the fiscal year 17 and 18 timeframe. From this list of current organizations, you can see the level of interest in this activity. There's still a lot of work to be done, and there are a number of people actually working very hard, volunteering their time. But the SOSA Consortium would certainly welcome any help and wisdom from firms engaged in ISR systems and technology development. So please feel free to reach out to the email address shown here with any comments, questions, or offers of support. And thanks, everybody, for your time. John?
Thank you, David. Excellent overview on SOSA. Just a reminder to the audience to keep your questions coming in. After our final and third speaker, we will start the Q&A session. Now, let me turn it over to our next speaker, Marc Couture of Curtiss-Wright. Marc?
Thanks, John. So how are sensors actually driving processing decisions in the year 2016? And having been in the business for a while, as are some of the other speakers here, there's different challenges these days, very interesting ones too. So what kinds of questions do COTS board vendors and subsystem vendors like Curtiss-Wright get these days for sensor signal processing? So I'm going to cover some of the hard issues and questions that our customers are seeking advisement from us on, and some of the trends and sometimes misconceptions with processor technologies and form factors. So first of all, a few seemingly random numbers here. 129,262. Well, I always find this fascinating. So one of our existing dual Xeon D modules, so there's 24 cores here, this has the same amount of floating point processing power as just a little over 10 years ago as 29 quad power PC cards. And so if you actually had to power 29 power PC cards, you would need a Honda generator. This particular one does do, I think, up to 2,400 watts. So with these advancements, why aren't COTS board vendors out of business? So the algorithms continue to get more and more sophisticated as the processing headroom rises. That helps. But it is really the continued evolution of sensors that is driving the increased need for processing. So wider bandwidths, more channels, greater resolution, and this in turn enables more sophisticated algorithms. So algorithms that might have been shelved at Sandia or MIT Lincoln Labs due to insufficient sensor resolution and or processing headroom can now come off the shelf. And the board count, the VPX chassis, it's not collapsing. It's kind of staying the same or even going up. So a little bit of a diagram map of ISR kind of meets EW and just some example programs of some of the more modern sensors. And these will all continue to evolve. In the upper right-hand You see, for instance, in purple there, the EOIR, and just an example of like an MQ-9 Reaper or a Predator with a high-end EOIR camera, focal plane array with the gimbal underneath the front. We continue along to the left there, the J-Star SAR, the canoe under the front, the Gator phased array there on the trailer, ground vehicle fitted with ample SIGINT apertures there, antenna, a King airplane with the ASIP comments system, very intense high channel count system, and a Growler with, look at all those EW pods, right? And those are continuing to be advanced. So, for instance, these are just some of the kinds of things we're starting to see at Curtiss-Wright, right? And the SIGINT, particularly comment, tuners, for instance, what used to be 20 meg to 3 gig. I think the comms band is widely accepted as more being up in the 6 gig realm with a lot of the superhat tuners. And just the 3U and 6U tuners from vendors like DRS, you see the channel count going from 2 to 4 to 8, right? So the filter technology, everything's becoming denser. For ELINT, the EW range, a classic range, 500 meg to 18 gig, now expanding to 27 gig. Wider IF on these tuners, and the channel count is going up on getting denser on them as well. Radar systems, narrow band to more wideband radars with digitizing right at the phased array, right, element by element. A lot of data coming off of that. EOIR, megapixel cameras evolving to gigapixel, so just many channels of high-rate fiber ingest. And then finally, EW, you just see with the ADCs and the DACs, higher sampling rate, higher resolution of the effective number of bits. It's just incredible, right? So the data rate coming in to these sensor processors, and once again, because the resolution's higher, there's wider bandwidth, the processing has to keep up with it. And I believe it is. So some of the typical questions and considerations we get when we have developers and different programs coming to us, right? SWAP, size, weight, and power. So what are the payload parameters? There's a big difference between, for instance, a shadow UAV as opposed to a global hawk. Channel ingest, is it analog or is it digital or is it both? How much? Is it coherent? Heterogeneous processing, we'll spend a bit more time on this. What's most appropriate? Is it FPGAs, general purpose processors like Intel processors, GPUs from NVIDIA? And then form factors, of course, VPX, probably the most popular modern form factor. Does 3U make more sense, or 6U? We're going to talk about that. Air-cooled, conduction-cooled, something more exotic. Sometimes that's dictated by what the payload can supply. Common sensor processing system model. So quite often a high bandwidth heterogeneous model where you have a massive sensor ingest. Often FPGAs are the first to get hit with that. Sometimes general purpose processors like Intel are more appropriate with the AVX units. And then if there's an algorithm that needs a teraflop of acceleration, a GPU might make sense. A lot of the systems we have are coherent channel models. So not only are sample clocks across different channels made coherent, it's also the scatter, gather, flow down of subsequent DSP stages need to be coherent. And then finally, I think sensor fusion's been talked about for a long time, but we're really starting to see it with the cross-queuing applications and superimposing of metadata. So SAR imagery superimposed with time difference of arrival, RF emitter data superimposed with EOIR, high-resolution data. You need a lot of processing to keep up with all of this ingest. Okay, so, all right, just a little bit on heterogeneous processing. So what dictates the choice of processing technologies or combinations of heterogeneous silicon? So you see some of the bullets there. Sometimes, the best application match for a compute element, digital down conversion, sometimes FPGA is very good. Sometimes very large FFTs where floating point resolution is required, even double precision, GPGPUs might be right, or if there's something where there's a lot of branching conditional statements, tracking, Intel may be best. Often the constraints placed by the payload, you need a combination of these things where you're playing to their strengths, and that may dictate the particular combination. Quite often, it's not technology. It's what do you have available for as engineers. You have one FPGA engineer and a bunch of CUDA GPU engineers, or the reverse. That may help dictate it. And then sometimes productivity and schedule. It's you'd like to do it in an FPGA, but you may not have the time. So it's a trade game of a lot of different levers here. So one device in particular has been very popular for sensor processing this year, so the Intel Xeon D. And as in the case of FPGAs, the Xeon D comes in different sizes and speeds while maintaining a common footprint. So this means that board developers like Curtiss-Wright can build a single printed circuit board, but support multiple chip SKUs within the same family without changing that PCB. So the user can then adjust the levers and find the best match for the application. So, for instance, the number of cores is different choices. What clock frequency do you run that at? And the trade-off may be increased thermal design power. You can also choose certain SKUs that have extended temp, which is very nice for very rugged apps. Now, if we look at some examples of models, sensor processing models, a coherent channel diagram here. So let's take a look at this 5-slot 3U VPX example here, which could execute a 12-channel TDOA, so time difference over arrival emitter locator, right? So we have a sample clock distribution XMC mezzanine on a Xeon D carrier at the bottom, feeding 3 quad ADC channel XMC modules, each with their own respective Xeon D on a 3U carrier. Each XMC has a Xilinx FPGA, so all 12 digitized channels are coherent, aligned on the rising edge of the sample period. So there's 4 times 12 Intel cores. There's 48 cores in total sitting behind these FPGAs to assist in signal ID and extremely precise emitter geolocation. So there's PCIe interconnect over the data plane, which these days with our Curtiss-Wright systems, we're using Dolphin, software from a company, Dolphin, that abstracts the complexities of PCIe data transfers, and it uses the DMA engine in the Xeon D. And then there's a 10 gig switch there. One of the big things in 3U that's kind of changed for sensor processing systems, the 3U has gone from 1 gig on the control, it's moving to 10 gig, largely in part to the Xeon D having it native to the chip. So we're starting to use precision time protocol for very precise alignment further downstream from the ADCs. So if you haven't heard of precision time protocol, this is worth paying attention to. That this is about having nanosecond synchronization across systems or remote systems of systems. And this isn't just in defense, right? This is coming out of the financial nanosecond trading industry. So you see the smaller example of the coherent sensor processor we were just talking about in the previous slide being synchronized with a mission computer and some other subsystems via PTP. In the bottom diagram there, that's just giving you a snapshot of how propagation delays are accounted for as Ethernet packets move around a system of systems. So we have a very nice white paper written by our defense solution CTO, Dave Jednek. Goes into great detail on some of the good work that we've been doing there and the PTP industry has been doing. Okay, perhaps an even more dramatic example of a high channel count system couples Curtiss-Wright Xeon D dual 6U cards on the right there with a 9-channel, one of our partners, DRS. They have a superhet tuner called Vesper, so it's a 9-channel tuner. So this system uses 10 gig Ethernet to transport VDA49 digitized IF from the tuners over to the Xeon D cards. So everything's coherent here. There's a couple of Curtiss-Wright Mellanox-based Ethernet switches in the middle between the tuners and the Z-on-D. So that's 54 IF channels of completely interconnected to the back-end processing where there's 144 Z-on-D Intel cores. So it's a great example of a very advanced sensor processing system. So in the home stretch here, 3U versus 6U OpenVPX. We get this question from a lot of folks, what's the best way to go? And there's a big motion towards 3U, but in many cases, 6U is more appropriate. And I think we're fairly agnostic here because we offer full Legos for both, if you will. And 3U in particular, where the board count gets too high, sometimes 6U may be better. And there's definitely instances where 3U are more appropriate. Often 3U is more swap compact, good with conduction cooling. Once again, 10 gig becoming prevalent on the control plane is a very, very good thing. And although we've been improving conduction cooling techniques, we've been pushing forward in VITA air flow through, which we've had on 6U. In the industry, we're now helping to push along a 3U variant of that to go where conduction cool can't go. 6U now, if you see that red oval across the connector on the 3U board and compare that to the 6U board, you see how much more backplane interconnectivity you get with 6U. So 40 gig E, PCIe Gen 3, and being able to have two tightly coupled processors on a single card. There are advantages there, of course. Two big challenges in 2016 and beyond. We've been hit with this. All of the companies here understand what I'm talking about. Folks on the phone, regardless of 3U or 6U, heat is a big challenge, and signal integrity. So the TDP, thermal design powers of these processors, in all the categories, FPGAs, GPPs, GPUs, these parts are getting hot. Some of them throttle, like the Intel parts and GPUs. So to get conduction cooling and air cooling, get more out of that, we're experimenting with and deploying new thermal interface materials, but air flow through in some cases makes more sense to go even higher. On the signal integrity side, the classic RT2 and RT2R connector, which is the staple VPX connector, everybody's starting to go above 6 1/4, which was its original design intent. So we have customers deploying on platforms with Gen 3 at 8 and 40 gig at 10, and we're even looking to get beyond that with the same connectors. So very exciting stuff. And last but not least, software scaling with modern-day sensor processing, right? Just 6 of these dual Z-on-D cards, that's 144 cores, right? And I drew it out there. It just gives you an idea. So managing such massive clusters requires that developers evolve past printf statements and VI, right? So powerful visualization tools from the high-performance computing world. It's needed to characterize and profile data movement and memory usage. This is the key to managing sensor data movement and processing in 2016 and beyond. And John, I believe that is it from me. So thanks, everybody. Look forward to the Q&A.
Thanks, Mark. Good presentation on sensor processing. And once again, before we get to our next speaker, who is also our last speaker, that after he is done, we will start our Q&A. So get your questions ready. And now I will turn over to our final speaker, Rodger Hosking of Pentek. Rodger, take it away.
All right, John. Thanks very much. And thanks, everybody, for joining us today. Pentek, as you may know, has been doing this kind of business, that is embedded signal processing with tightly coupled front ends for wideband signals coming in, and many of them from sensors. We've been doing this now for 30 years. So today what we're going to do is present some of the challenges that we see our customers bringing to us to help them with their solve their sensor ISR sensor problem, and then some of the solutions that we found to be very useful in tackling them. So what are some of the challenges? I think we've heard them. You know them yourselves. we've got much more traffic. We've got wider bandwidths. We've got wider dynamic range requirements on all of the sensors that are being acquired these days. And in terms of the processing load, which we just heard about from Marc, you need to fuse a lot of different sensors. You need to classify the signals. You need to extract information through decoding, decryption, demodulation, and often combining many channels together in things like phased array receivers. And the problems that all of these tasks involve, of course, you have interference, co-site interference, for example, on board a ship. You have security issues. You have health monitoring concerns about how healthy is your system. And then there's reliability and, of course, the adaptability, so you can use the same platform for different applications without starting from scratch. And then finally, of course, the swap effects as well. These are all on top of each other in any particular system that a customer presents to us. And these challenges can kind of be amplified, if you want, if you try to put a lot of those same kinds of sensor systems into a small space. Even if it's a relatively large UAV, you are competing for size, weight, power. You're also competing for signal space. And you're competing for places to put your antenna. You're competing for different weight constraints and power constraints and so forth. So this can be really a difficult problem depending on the platform. It's highly dependent on where your system is going. Some of the things that drive the sensor platforms, as we said before, the wider bandwidths for video information, for communications, and SIGINT, ELINT, radar, and so forth. These all require higher sample rates. They require wider bandwidth signals. There's a lot more traffic out there. There are more signals that need to be acquired every day. And in order to capture those signals, you need faster A to D converters, D to A converters, wider bandwidth sensors. In order to process the signals that come to the processing engines, you may need FPGAs or very high performance processors. But FPGAs are still often the only thing that can handle the tasks that you need to do as close to the antenna, as close to the sensor as possible. So all of these fast sensors and data converters and processors then need to have the interconnections between your system elements become much higher, to support much higher data rates in order to accommodate the transfer of data and the signal processing links from the sensor all the way down through perhaps the operator at the end of the chain, who's actually going to act on the information that's being acquired in real time. These all then have to have those fast links. So based on all of these challenges, what are some of the things that we have found to be very successful? First of all, we use quite a bit of XMC technology. This is the mezzanine card that's based on the venerable PMC, of course, but now, of course, with XMC, it's migrated to gigabit serial interfaces. We find that XMCs are prevalent throughout the industry. Many of them, and virtually all of ours, include onboard FPGAs to do the local FPGA real-time signal processing, like digital down conversions, for example, that might occur after a very wideband A to D converter. And having that FPGA right there next to the A to D converter on an XMC, and then have it support a very fast PCI Express link to the rest of the system, is an extremely efficient way of solving that front-end processing. We have migrated through 3 different generations of XMC, starting with our Cobalt, which is the Vertex 6, the Onyx Vertex 7, the Jade, which is our new ultra-scale just introduced this past Monday, with a wide range of different A to Ds, D to As, digital I/O, and all with increasing, as you go through the families, increasing horsepower in the FPGA. So let's take a look a little bit at the families that Xilinx has brought to the marketplace over the last many years. Showing in this graph on the vertical axis, you have the number of logic cells in each of the different members of the family, which are shown as colored graphs on the solid graphs on the chart here. But each of those colors has different density devices within the family. So you can see that the number of logic cells has grown dramatically, especially in this latest version, the Pentek's UltraScale. These are all compared on roughly the same size package, so the density has improved dramatically going from family to family, each evolutionary step. And specifically, if you look at DSP, which is a big part of our customers' requirement, the number of DSP slices in the latest Pentek's UltraScale device is now 5520. These are complete DSP engines located on a single FPGA piece of silicon. So in the family that we just went through, the Cobalt, Onyx, and Jade, we have different members of the family which we offer on our products that have different numbers of logic cells and different numbers of DSP slices. What you can see from these charts is you can see that there's an excellent choice in terms of the range of resources across these three families of products. And they're scalable, each of these parameters, the logic cells and DSP slices, by more than a factor of 10, from the smallest to the very largest. This allows our customers to choose the most cost-effective solution for I/O and different FPGA horsepower requirements. The other really nice thing is it allows for new technology insertion. As you outgrow perhaps a certain task or you want to upgrade the system, you can put in the next generation of FPGA XMC module and use it to boost performance. Lastly, XMCs are extremely portable. They are available in XMC form factor. We have adapters that turn them into PCI Express boards, 3U and 6U VPX, 3U and 6U compact PCI, AMC, micro TCA, and so forth. It's all based on the same XMC module, but just with a lot of different family platform support. And if you compare the Pentek's UltraScale with the previous two offerings from Xilinx, Vertex 6 and 7, we see that the cost per logic cell and DSP slice has been reduced by 30 to 50%, and power dissipation reduced by up to 40%. So these new stages of FPGA evolution have really helped a lot. What's one example is, for example, a 3.6 gigahertz 12-bit A to D converter with built-in digital down converter. This is a XMC module that's been converted to a 3U VPX board with the high bandwidth A to D at the front end, and then with the FPGA doing the digital down conversion and other signal processing right next to it, all in the same XMC module. Extremely popular, powerful product line. One of the things that we've noted in the last few years is the transition for the new wideband data converters that use a new standard called JESD204B. This is now replacing the traditional parallel LVDS interfaces that go between the data converters and our FPGA with a new gigabit serial interfaces that are running at much higher rates, 10, 12 gigabits per second, that result in fewer PCB traces, so it actually simplifies the footprint of the copper traces on the board, and it gives you higher data rates and higher densities. The problem with JESD204B is that the data rates and the sampling rates are linked together, so that makes it a little bit more difficult. You're trading off flexibility for performance. But our new Jade product, the last XMC we looked at, has support for these links, so we can support the newest JESD204B devices. Another thing you'll find pervasive throughout most embedded systems for ISR is the PCI Express Gen 3 system links. In virtually every CPU, whether it's a motherboard or whether it's a 3U VPX CPU card, you will have a Northbridge chip that has high bandwidth PCI Express links to different slots and different peripherals and to memory. And these links are critical for sustaining real-time operation, where we use the DMA controllers in our boards to directly move data across PCI Express through the bridge into memory, and then the CPU uses the data that's been moved to memory as its processing target. So these are now extremely powerful and popular in most architectures you'll find in high-performance real-time embedded systems. Another thing that we found that solved a lot of problems in connectivity has been our optical interfaces, which are shown here for BPX in a 3U example. This is under a new standard called Beta 66.4. It allows you to take advantage of optical technology by replacing part of the BPX connector with an aluminum housing that contains a MT optical ferrule that contains, in this example, 24 different optical lanes. And when they are mated, the optical lanes, the ends of the optical pipes line up, and you have an interface from the module, which is shown on the top, directly into the backplane connector. It supports any protocol. It's protocol transparent. You can go between modules within a chassis. You can also go between chassis, from chassis to chassis. And this has now been a ratified standard. It's ANSI Beta standard, Beta 66.4, which was approved in May of this year. We take advantage of that standard in our Flexor offerings, which are 3U, BPX, and also PCI Express, to give you the combination of a carrier board for FMC, that's another standard in the industry, and the carrier, which is the FMC carrier. These two products, the FMC and the FMC carrier, are married together by Pentek with FPGA IP installed to allow you to take delivery of a complete system. We also have optional Optical Io on both of these devices. What we're doing is we're selling a combination of an FMC module with a carrier as a set, which we call a Flexor set. And these are the different model numbers of the FMC module combined with the different carrier, the 7070 for PCI Express and the 5973 for 3U BPX, with complete software support, with complete FPGA development tools. Everything is ready to go. There's no FPGA development required for many applications. You can use it right off the shelf. And the important thing about Flexor sets is you get support from a single vendor because you're getting the FMC module and the FMC carrier, both from Pentek fully. Now, some of the things that you can do with these types of systems is you can put together connections, as I mentioned before, between two boards using the optical interfaces from slot to slot within a chassis. You can also take the optical links and bring them out to bulkhead connectors on the back of the chassis, for example. This allows you to connect to remote subsystems using the optical link to join the subsystem, which could be located at some distance, to a sensor box, which could contain, for example, data converters and an optical interface where you're now able to digitize the wideband sensor signals and send those signals over optical links back down to the processing box. Nice advantage here is it works with very high data rates. There's no contamination from EMI signals that might be on the path, and there's no degradation of the signal over very long runs, unlike copper. And the cables are actually smaller, lighter, and even less expensive per foot than the copper equivalents. So it's a very, very good solution. We're finding a lot of customers migrating towards optical interfaces. So just to summarize my talk, what we're saying is that there are a lot of great COTS solutions based on standards that really are great for solving the toughest ISI system problems. We're using PCI Express Gen 3 extensively, and this really helps you to eliminate bottlenecks and data paths. We're taking advantage of the new FPGA technology. We looked at how you could reduce your cost, your horsepower, size, weight, and so forth. We're installing advanced DSP functions in the FPGA so that they're ready to use in the deliverable products. We're taking advantage of the new JESD 204B standards to improve the speed and the connectivity between the data converters and the FPGAs. And we're also allowing our customers to take advantage of optical interfaces, as we just saw, with all of their many benefits, and especially with remote sensors, especially ISR sensors. And so this whole offering then is, again, based on standards, open architectures. What this has, not only does it help you save costs, but it really simplifies upgrades for new technology insertion, and it really helps you fight against product obsolescence. So that's my last slide, and I'll turn it back over to John. Thanks.
Thank you, Rodger, for an excellent presentation. Now let's get started with our Q&A. We have some questions from the audience. Our first question will be for Rodger Hosking. Does the Pentek UltraScale FPGA on your Jade XMC run cooler than the earlier boards?
As a matter of fact, the power that's dissipated in the FPGA can be about the same, but again, remember you're getting perhaps twice as many resources. So when we say the power is reduced, we always talk about the power per function. But for a given number of watts, yes, it's reduced for function, but in many cases people will add more functions inside the FPGA to bring the power back up to about the same as it was before.
Thanks, Rodger. Next question is for Marc. Do you see PTP becoming more and more prevalent, and is it appropriate for the precision required by sensor processing?
John, it's I think for a long time, 1 PPS and NTP. Folks remember IRIG-B. Obviously the need to be coherent in these sensor systems. It's not new, but a lot of the Ethernet's become very prevalent in defense. For a long time it wasn't, and now it's fabric that's everywhere. So absolutely, and it's funny because PTP, I think I'd mentioned the financial industry, right? And they're companies that are very focused on nanosecond trading, and they care about a lot of the same things we care about in defense: high throughput, low latency, determinism, and coherency. So, we with our modern generations of products, including our switches and SBCs and DSP modules, and there's different levels of PTP, for instance. The version 2, the 2008 version, we've actually been doing quite a bit on that for sure.
Okay, thank you, Marc. Next question is for David. David, is SOSA intended to cover just airborne ISR requirements and platforms?
No, I think the initial activity that started it was primarily driven by airborne ISR, but the objective of the working, or the consortium, I should say, is to be agnostic to the modality, to the platform, whether it's airborne, naval, or ground. So the intent is to be agnostic across those different domains.
Okay. Next question is also for David. How does SOSA group activities and goals relate to FACE activities and goals? Do they overlap?
So there is some overlap. I don't work in the software working group. There's a software working group activity that's looking at that, but they are looking at all those standards. There's an intent to try to harmonize between what SOSA is doing and FACE. So SOSA really doesn't want to develop new standards. They want to adopt existing standards and only call out new standards if it's absolutely necessary. So I think what you're going to see largely is that SOSA will adopt existing standards like FACE or the modular open RF architecture, MORA, and other standards. So they're working very hard from a software operating standpoint to address commonality across those other standards activities.
Thank you, David. Next question is for Marc. How does one carve up an application across FPGAs, GPPs, and GPGPUs?
So I kind of discussed some of the different, trades during the presentation, but so part of the answer is play to the strengths of the individual devices, right? So for instance, FPGAs, they're I/O chameleons, right? They're superb for very low latency applications. That's why you see them in electronic warfare for DERFMs, for instance. General purpose processors like Xeon Ds are great for that. They have nice vector math because of the AVX SIMD engines, but they're also very good for highly multi-threaded, branched, conditional type functions that FPGAs and GPGPUs just can't handle that sort of thing in general. Things are changing, though. GPGPUs, though, for sure, are massive pipelined floating point engines. So when there's a big hunk of your algorithm could really use some teraflop power, that's quite an engine to go with. But what's really neat these days, right, you have a lot of folks using MATLAB and Simulink, and then there's OpenCL, which is kind of a holy grail of being agnostic across these heterogeneous processing technologies. You can actually characterize how it performs on different types of engines and figure out how you divide and conquer.
Thank you, Mark. The next question, speaking of tools, is for Rodger. Can you share, are there any development tools for the new Jade XMC?
Yes. We're focusing mostly on hardware for this presentation, but in fact the Jade tool has a brand new suite of software development tools from Pentek called Navigator, which includes a board support package and a new FPGA design package that is designed to work directly with the latest Xilinx Vivado design tools, which takes advantage of the block diagram FPGA design techniques using standardized blocks that are now become the standard way of encapsulating IP, that each of the blocks has AXI4 interfaces to make the interconnections between all the different IP modules as simple as click and point. You draw a line from one block to another block, and the tool takes care of making the AXI4 connection. So it's an extremely very easy to intuitive graphical representation of a very complex design that previously people had to wade through lines and lines of code. Now they can see the graphical representation of those functions, and it really speeds development. So we're quite excited about that. That's all available on our website. Thank you,
Rodger. Next question from the audience. This one's up. We're going to go back to Mark. Can the VPX backplane with the RT2 connectors handle PCIe Gen 3 and 40 gig over temperature and vibration? And they also ask about if there are even higher rates. Mark.
Yeah. So we're probably Curtiss-Wright on its single board computers, SBCs, and switches, for instance, where we tend to use a lot of PLX switches and Mellanox devices and so on. So there's quite a lot of the OpenVPX expansion plane and data planes. A lot of this, right? And you can, in a large system, there's a lot of traffic at varying lengths. So one of the things now, we're at a point where we're well past development. Some of these products, some are in LRIP on multiple different platforms. And we do a lot with, for folks in the audience familiar with Vita 47 testing, where we cycle a lot of this. For instance, Vita 47 has something called ECC4, which there's 500 cycles with certain dwell times. And we test I/O. We test this I/O, so we're quite confident in Gen 3 and 40 gig. And now the real trick is with PCIe Gen 4 coming out, and and other protocols. What's next? 14 gig, 16 gig, and we're looking to see how far we can get with the RT2 and RT2R connector before we actually, as a Vita community, have to move to something new. So we're seeing some good success there so far.
Thanks, Mark. Next question is for David French. David, you answered an earlier question about SOSA being exclusive to Airborne, and you said no. So will SOSA be adopting the Victory standard at all, which is used for distributed computing and vehicle electronics, or Vitronics?
Yeah, again, the consortium activity in the working groups, it's still very early stages. And again, the objective is to adopt as many existing standards activities if it fits within the SOSA objective as possible. So again, Victory, the Mora standard, the modular open RF architecture is part of that. So yes, there's an effort to harmonize the objectives of SOSA with the existing standards community. both from an airborne, ground, be it victory or face. So that activity is going on, very early stages, and that is still the objective of the consortium.
So SOSA, more, I guess the best way to say it is not creating standards. It's basically it's building a bridge with all the other commonality efforts out there.
Exactly, and if there's other new standards that have to be developed to meet their objectives, that will be considered. But the priority is to use existing standards. I'm sorry.
Okay. Next question for Rodger. Don't optical interfaces add a lot of power and cost?
Well, a long time ago they used to. Today, in terms of cost, the optical interface is probably somewhere between 5 to 10% more than the cost of the product without it. And the power is maybe 2 or 3 additional watts. The nice thing is that there's so much momentum now in the industry towards using these standards, is that the connectors, the transceivers, the emitters and detectors, and so forth are becoming easier to use, easier to package, and lower cost. So this is a trend that's definitely going to be headed in the right direction.
Okay. This will be our last question, and anyone feel free to answer it. What types of military applications do you think will be the best bets for the next couple of years for embedded signal processing suppliers and their solutions that you talked about today, despite the uncertainty with the upcoming elections? Are there certain things, are there things for certain where they'll need the signal processing regardless of what happens in Washington? Who would like to go first?
Well, I can chime in. I think it doesn't take too much of a crystal ball to understand that our need to get better signals intelligence, communications intelligence, to get radars that can detect targets that are farther away and smaller, and the ability to handle a bewildering complexity of the electromagnetic spectrum that we're faced with today to try to make sense out of it. These things are driving strong driving factors for survival of our country and our armed forces and so forth. I think that all of those and each of those are going to be strong markets for all of us in the next few years.
Anybody else want to add to that, or?
Yeah,
John, this is
David.
Go ahead, David.
Yeah, David with Abaco. I'd probably reinforce that. I mean, if you look at, it's a big priority when you hear the DoD talk about offset, that you have to be able to listen to and manage the electromagnetic spectrum. So it's going to be a funding priority, I think, for well into the next decade, because of anti-access aerial denial kind of capabilities, and I think it's going to be well funded in a very strong market for the foreseeable future.
Okay, and Marc, you had something to say as well.
Yeah, no, I think the interesting thing I've been seeing, I kind of mentioned it, right? I think everybody here, we've heard the term sensor fusion for some time, but I actually see the rubber hitting the road, right? And the infrastructure is there with things like PTP and everything that Rodger was saying and so on. There's just so much more data. It's very high precision, and being able to queue this up, from a standoff position, it's going to be pretty critical moving forward.
All right. Thank you, gentlemen. That brings us right up to our time limit for today. Sorry we cannot get to all of your questions. Someone may get back to you after the ECAST with more information. I'd like to thank David French, Marc Couture, and Rodger Hosking for speaking today, and Abaco Systems, Curtiss-Wright Defense Solutions, and Pentek for sponsoring the event. And just another reminder that this and all OpenSystems Media eCast are copyrighted and may not be recorded or used in any way without the express written consent of OpenSystems Media. This eCast will be archived online today and will be available for 1 year. There will also be an MP3 version of the event available. I thank you all for attending and look forward to seeing you on future OpenSystems Media eCast. Goodbye.